So far, we have been talking about classical results. Today, we will talk about concepts that were introduced in this century, Plabic graphs. These were introduced in 2006 in a paper called Total Positivity, Grassmannians and Networks by Posnikov. This paper has been cited over 400 times according to Google. Some applications outside of math, according to Wikipedia, would be in quantum physics, computer vision and face and shape recognition, and a data visualization technique called Grand Tour. So first, some definitions. A graph is called planar if it can be drawn in the plane or on a piece of paper in such a way that the edges do not cross. For example, the complete graph on 4 vertices. Normally, we draw it like this, but we can also draw it in this way instead. So K4 is planar, but K5 is not planar. A Plabic graph. So Plabic stands for planar and bicolored. A Plabic graph is a graph that is drawn inside a disk it has n boundary vertices on the boundary of the disk. And n boundary vertices are labeled 1 through n in clockwise order. The Plabic graph also has internal vertices. All internal vertices are colored down. One color would be shaded like that, and the other color is not shaded or empty or white, depending on the pen that you're using. And for what we will do, we'll assume that the Plabic graph we're working with is a simple graph. So no multiple edges. So no multiple so for example, this would not be allowed. And also no loops. We also assume that no vertices of the same color are adjacent. Note that this is the same restriction as saying that we want a bipartite graph for the internal vertices. We also assume that the graph is connected. And assume each boundary vertex is adjacent to a single internal vertex. And we assume no leaf except for the boundary vertices. Remember that leaf is the degree 1 vertex. For example, this is a Plabic graph. So here we have the boundary vertices be 1 through 6. So notice that so far I'm drawing internal vertices in such a way that they are bipartite, or so no, if two vertices share the same edge, then those two vertices should have opposite colors. Alright, so next I want to define rules of the road. The rules is that when you are walking along the Plabic graph, you would turn maximally right at the black vertices. So if I'm walking along here and I see a black vertex, then I would turn maximally right, so that will be this way. If I see a white vertex, then I will turn maximally left, and that will be this way. Given a Plabic graph, starting from J. And recall from the set of 1 through n to itself. And often we use a two-row notation. So for example, if you have a function f where 1 is sent to 3, 2 is sent to 4, 3 is sent to 5, 4 is sent to 1, 5 is sent to 2. we can write it in this 2-row notation. Let me write another permutation here that has a fixed point. So here 1 goes to 1, 2 goes to 4, 3 goes to 3, 4 goes to 2, and 5 goes to 5. We also have a 1-row notation. So for F, we would just write the bottom row, 3, 4, 5, 1, 2. And for G, the bottom row is 1, 4, 3, 2, 5. And 1-row notation. So let's first write this in 2-line notation or 2-row notation. So I know to write 1 through 5 because here there are 5 boundary vertices. So starting at 1, I go to the first vertex and I see a black vertex, so I turn right. I see a white vertex, so I turn left. I see a black vertex, so I turn maximally to the right. I see a white vertex, so I turn left. Black vertex, I turn right. So I am at the boundary vertex 3. So that means 1 will be sent to 3 for the trip permutation. So now let's compute the trip from the boundary vertex 2. So the first vertex I see is white. So that means I have to turn maximally to the left. I see a black vertex, so I turn to the right. I see a white vertex, so I turn to the left. And I end at 4. So that means 2 goes to 4 in the trip permutation. So the picture is getting crowded, so let me make a new copy. So now I start from the boundary vertex 3 to figure out what the trip would be from 3. I see a black vertex, so I turn maximally to the right. I see a white vertex, I turn left. I see a black vertex, I turn right. I see a white vertex, I turn left, and I end at 5. So 3 goes to 5. Now the trip from 4, the first vertex is white, so I turn left. I see a black vertex, I turn, oh sorry, so because first I see a white vertex, so I turn left, and then I see a black vertex, I turn right, and I see a white vertex, I turn left, I see a black vertex, I turn right, I end at 1, so 4 goes to 1. Now I want to figure out the trip from vertex 5. So first I go to the first vertex, it's white, so I turn right, or sorry, I turn left, and then I see a black vertex, so I turn right, and I see a white vertex, so I turn left, and I end at 2, so 5 goes to 2, and this is the trip permutation for G1. And now I want to talk about local moves on Plabic graphs. The first one is called, or let's label the first one M1. This is called a square move. If G has a square formed by 4 degree 3 vertices, then we can change G by switching the colors of these 4 vertices to the opposite colors. And if we just swap the colors, then the graph will no longer be bipartite. So we add some degree 2 vertices to preserve the bipartiteness of the graph. So if locally the graph has this square face, then I can apply this square move. So I change the colors of the vertices to the opposite colors. But if I just do that, the rest of the graph will no longer be bipartite. So I have to add these degree 2 vertices so that the rest of the graph will continue to be bipartite. So this is a two-sided arrow, so I can go from the left picture to the right picture, and I can also go from the right picture to the left picture. Another local move, M2, is where we can contract or expand a vertex. Any degree 2 vertex V not adjacent to a boundary vertex can be deleted and the two vertices adjacent to V merge into one vertex. And again, this operation can be reversed. So if I have a situation like this, where I have this degree 2 vertex and it's not adjacent to a boundary vertex, then I can apply the M2 local move, where basically this vertex is deleted and then the two vertices adjacent to this white vertex are basically glued together to become one vertex. So I would get this local picture, and this would work also if the degree 2 vertex is black. So one remark about M2 is that this local move M2 can be used to change a square face of a Plabic graph G into a square face whose so this is any square face of G can be turned into a square face whose four vertices are degree 3. So for example, I might have a Plabic graph that looks, say, like this. I can then apply M2 on, say, this vertex. And maybe to make it more clear what's going on, I'll change the position of the two Plabic graphs. Oh, so on the right is like the situation where I have fewer vertices, and on the left I will add more vertices. So locally, what I have circled in green on the right turn into locally this part that I have circled in green on the left. And the last local move is where you insert or remove a middle vertex. So what this does is that we can remove or add degree 2 vertices as long as the graph remains bipartite. So if I have this situation locally, I can apply the local move M3 and just remove this degree 2 vertex. I'll just have this line. And it doesn't matter what color the vertex is. For example, let's look at the bipartite graph G1. Let's say I want to apply the local move M1 and I want to apply it to this square face on the right. So what I would do then is replace the colors of the vertices. So I change to the opposite colors. But I also add a degree 2 vertex for each of the 4 vertices. And now I look at the rest of the vertices. So I still have these other 2 internal vertices, and this white vertex should connect, should be adjacent to the boundary vertex 2 and to this other internal vertex. So I connect this white vertex to the boundary vertex 2 and also the internal vertex that is black. And similarly, this black vertex is connected to the white internal vertex, and then this black vertex connects to the boundary vertex 3, and this white vertex connects to the boundary vertex 4, and then the rest of the graph should be the same. Okay, so now let's see what other moves we can do to reduce the number of vertices. Let's see if we can apply M2. In order to apply M2, we would need to have a vertex which has degree 2 and is not adjacent to a boundary vertex. So no, 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 and no, but we can apply M2 to this vertex. So basically we would take this part, we would remove the middle vertex, and we will connect these two adjacent white vertices and turn it into just one vertex. And the rest of the graph would be the same. So this whole thing would be one big vertex. And it was white. So the picture would look like this. And we can also apply M3. We can just remove this vertex and this vertex. Oops. So this edge here would be, let's say if I say this is 2, this is 1 and 2, this would be the edge that I have marked. And this black vertex would be connected to this white vertex. And this white vertex would be connected to a black vertex. And I want to remove the vertex that is adjacent to the boundary vertex 3. So I would have this situation and this situation, and then the boundary vertex 5 would be connected to this white vertex. So I would have this picture. All right. So here's a proposition related to the trip permutation. The trip permutation is preserved by the local moves M1, M2, and M3. So we can check, so let's call this new graph G2, we can check that the trip permutation for G2 should be the same one as the trip permutation for G1, which we already computed to be 3, 4, 5, 1, 2. So let's prove it. So for M1, so let's say we have a trip going this way. So in the left local graph, I would turn right because I see a black vertex, and I turn left and I turn right. And in the local graph in the right figure, I should start the same way locally, and I see a black vertex, so I turn right. I see a white vertex, I turn left. I see a black vertex, I turn right. I see a white vertex, I turn left, and I see a black vertex, so I turn right. So locally, you would get the same effect. So this is the proof for M1. You should finish the proof and then check for M2 and M3. All right, so a big theorem that was in the paper that I mentioned earlier, theorem 13.4. So if two Plabic graphs, let's say G and H, have the same trip permutation, then we can get from G1 or from G to H by applying a sequence of the local moves M1 through M3. Location was 3, 4, 5, 1, 2. And so another definition, a source face labeling of a Plabic graph G is the following map from the faces of G to the set of subsets of the set 1 through n. So here's the map. For each trip from I to some other boundary vertex J, we place the label I in every face of the Plabic graph, which is located to the left of the trip I to j. So let's look at this example using G1. So let me have another picture. All right, so let's do that in order. So I'll look at the trip from 1 and then 2 and then 3, 4 and then 5. So the trip from 1, we already looked at that earlier. So turn right and then left, right, left, right. And so this side is the right side of 1, but I want to place the label 1 in the faces which are to the left of 1. So I put 1 in each of these 4 faces. So 1, 1, 1, 1. Let me do that here. And then the path from 2, the trip from 2, I see a white vertex, so I turn left. I see a black vertex, I turn right. I see a white vertex, I turn left. The left faces, so the faces that are to the left of the trip from 2 to 4 are these faces. So I write down 2 in those faces. Now let's look at the trip starting at 3. So I turn right, and then left, and then right, and then left. So the faces that are to the left of 3 are over here, or to the left of the trip from 3 are these 3. So I write down 3 on those faces. Let's look at the trip from 4. I see a white vertex, I turn left. I see a black vertex, I turn right. I see a white vertex, I turn left. I see a black vertex, I turn right. So the faces that are to the left of the trip from 4 are these faces. So I write down the number 4. And we just need to check one more trip. Let me use the color orange. So from 5, I see a white vertex, I turn left. I see a black vertex, I turn right. I see a white vertex, I turn left. So I finish at 2. And the faces to the left of this strip are these 2 faces. So I will write down 5 there. So 5, 5. So this over here is the face labeling for G1. And so for exercise, please follow what I just did to compute the phase labeling for all of these 5. And I have already computed the one for G1. And in fact, all of them will have different phase labelings. All right. So like I said earlier, these are the only Plabic graphs that you can get with trip permutation 3, 4, 5, 1, 2. And there's a theorem that the Plabic graphs with trip permutation 3, 4, 5, 6 until n, and then starting at 1 and then 2, are Catalan objects. So when n is 5, you get 5, and actually when n is 6, you will get 14. And so here are the 5 triangulations of a 5-gon, and we know that triangulations of a polygon are Catalan objects. So the question for the homework exercise is, do you see a natural way to map the 5 Plabic graphs the ones with the trip permutation 3, 4, 5, 1, 2, these 5, to these 5 triangulations. So if you see it, explain what this map should be. And it should be a natural map so that it could be generalized for all n. If you